Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so let's get started. It's really my great pleasure to introduce Greg Hager. Greg is a professor and also chair of Computer Science Department at Johns Hopkins University. Johns Hopkins, is very well known for medical things. Greg used to work in computer vision for general robotics, but later more evolved into vision for surgical robotics, I guess. Mm-hmm. And he has been interested now in a lot of other things like interactive large display. And today he will talk about collaborative computing in the physical world. Greg?
All right. Yeah. Thanks, Xinyu. It's a pleasure. Thanks for all of you for coming today and listening. So when I was putting this talk together, I kind of chose the title intentionally to change a little bit the thought pattern of the usual talk I give, which tends to revolve around collaborative systems, specifically in robotics. And I wanted to kind of broaden it a little bit and think more about collaborative computing beyond robotics, including robotics, but really computing in the physical world. And part of what I started to think about as I was putting it together is, what's the difference between where we are now in computing research in this area, and where were we roughly a decade or a decade and a half ago. So this is actually, this is a slide for Rick. So this is work that came from my lab really around, I guess, the mid-1990s to 2000 time frame. And I guess the interesting thing to me really is a lot of the things that I see today were going on back then. We were talking about them. So we've got, this looks suspiciously like what I guess used to be called the Microsoft Surface that we were developing in the lab, gesture-based interaction, real-time feedback from robotics. If any of you remember Kentaro Toyama, he actually built that video game that you just saw go by there, so interactive video games. So certainly both human-machine interaction using perceptive devices and robotic interaction with the physical world using perceptive devices was out there. So why is today different than what we were doing back then? And I think there's a really simple answer, which is computing has won the war. If you look at what we had in terms of computing platforms and in terms of sensing and robotics 10 or 15 years ago, it's wildly different. So as you all know, we've now got computers winning Jeopardy. We're all carrying supercomputers in our pocket. I actually checked, so that's about equal to a Cray 2 for anybody who actually cares. And computing is just showing up anywhere. This is actually a shot from Johns Hopkins sitting outside the OR. That's what people are doing, using their computers. And of course, obviously, people think about computer-aided diagnosis. This, I think, might actually also be from Kentaro. It's third world education. Yep, MSR India. And of course, now in entertainment, practically everything lives on computing. It's pervasive. In fact, just to check it out, I looked to see how many computing devices are there in the world, and I'll just define that as microprocessors. And so, as close as I can guess, there are somewhere between 50 and 100 billion active microprocessors in the world right now. So, like, what does that work out to be? 10 to 20 microprocessors per person on the face of the earth. So if this were a virus, we'd be looking for an antidote, or a form of life. We'd be worried about it taking over. And it's just continuing to grow at remarkable speed. The other thing that's different is platforms for input. So of course I'm at Microsoft, and so I have to give Microsoft credit for really changing my life over the last 2 or 3 years by introducing the Kinect, because suddenly you've got a low-cost, easy-to-use platform that gives you direct 3D perception of the physical world. And of course, originally introduced for gaming, which is a lot of fun. My kids certainly enjoyed it. But in my life, just about everything I knew suddenly grew a Kinect. So robots sprouted Kinects. There's actually Kinects in the ICU at Hopkins right now observing patient care. And this is actually a video that almost went viral from our lab, where we're running a Da Vinci surgical robot from a Kinect. And again, this continues to grow. There are probably 20 Kinects in my lab at this point doing just about anything that you can imagine. So we now have a rich source of input to connect to all this computation. And in fact, it's not just the Kinect. There's every form of input known to man. So accelerometers, gloves. Every laptop now has a camera. You wear a fuel band and decide how much you move today. So the world is just now connected to computing in a way that it was never connected before. And the same on the output side. So this is a set of platforms that I can now get in my lab. And again, 10 years ago, none of these existed. But now you can get the Willow Garage PR2. That's the DLR Justin robot, just a crazy mechanism in terms of what it can do. NASA Robonaut's actually up in the space station right now. And many of you probably saw in the New York Times the discussion of Rethink Robotics, which is a new low-cost manufacturing platform that's actually just being introduced by, Rethink Robotics, a company founded by Rod Brooks. So we have not only just the input and the computation, but the output is there as well. And so it really makes for an interesting mix. And furthermore, it's actually having practical impact in the real world. So for those of you who don't know this is the Intuitive Surgical Da Vinci system. It's a commercially available robot that does surgery. Right now, there's about, roughly speaking, 2,500 of them installed around the world. They do in excess of 300,000 procedures a year. And for example, if you go to get a radical prostatectomy, odds are better than 80% that it's going to be done through a robotic surgery as opposed to traditional open or laparoscopic surgery. And those numbers continue to go up. So it's very rapidly becoming a standard of care in certain areas. Now, so that's all great. And I think this really exemplifies the opportunities that are out there in connecting people with really computational systems. What's missing here, I'll get rid of the bloody slide. What's really missing, though, is kind of the level of interaction that's going on there. So, everyone's familiar with traditional robotics, which grew out of automation research. So it's a programmable controlled machine. It's writing a program just like you write Microsoft Excel. It just happens to take place in the physical world. The other extreme is the Da Vinci robot we just saw, which is strongly human interactive, but it's direct control. There's really no intelligence in the machine whatsoever. It's there just to replicate hand motion into the patient and to transmit light back to your eyes so you can see what's going on. And it really promises to do nothing else in between.
Force feedback as well?
There is effectively no force feedback. So it's really, and that's actually not unusual in laparoscopic surgery, that you don't get a lot of force feedback in the system.
So is the main advantage of using this robotic system the sort of rescaling of the surgeon?
No, it's actually, it's more subtle. So the longer story is this. So we started out with open surgery, where you could put your hands inside the patient and you could do anything you wanted. Then in the 80s, we went to laparoscopic surgery. And what did we do? We separated the surgeon from the patient using tools, but those tools are pretty much straight chopstick tools. And so when you introduce the robot, you introduce two things. The first is you get stereo visualization, which you don't get in laparoscopic surgery. And the second is you get a wrist inside the patient. And so suddenly you can do all types of reconstruction surgery, or reconstructive surgery, I should say, that you can't really do comfortably with traditional laparoscopic tools. So you can sit down ergonomically, you feel like your hands are in the patient again, you can see in 3D. It's just a completely different platform, again, really, for people to think about surgery. And part of the game has been for people really to relearn and to rethink how you can do surgery when you've got that kind of a platform available.
So it's better than just using real hands? Or it's better than...
Well,
doctor's still there, right? You don't really save labor.
It doesn't save labor, but so to begin with, it's minimally invasive. So the big thing is, with minimally invasive surgery, you're reducing blood loss, you're reducing morbidity of the patient, reducing scarring. So it has all the advantages of traditional laparoscopic minimally invasive surgery. And then it actually has two really key advantages, I think. The first is, as we said, you have additional dexterity in the patient, so there are things that are just much easier to do with it. And the second is actually it's a lot more ergonomic for the doctor. So if you look at certain areas of the medical profession, they have some of the highest rates of back and neck injury of any industry. And it's because, I know surgeons who have 18-hour procedures. They just stand there for 18 hours in usually something that's not particularly ergonomic. So it provides a lot of interesting possibilities.
Essentially, they get little tiny hands.
Yeah, exactly.
They become almost little tiny surgeons that can go.
Yeah. And it's actually, it's called intuitive, and it is intuitive. When you sit down, you could sit down, and within 10 minutes, you would very quickly understand what's going on because it feels like your natural hand-eye coordination. I feel like I'm an ad for Intuitive Surgical here. But so the key thing, though, is so we're transmitting the surgeon into the patient, but we're not really augmenting the surgeon in a real way, except perhaps for some motion scaling. And so a lot of what we've been thinking about is, well, how do you operate in kind of this mid-space where, what you can imagine is in structured environments, we can do a lot of autonomy. In unstructured environments, like surgery, we have the humans strongly in the loop. Are there places where we can kind of find a middle space? So, for example, if you're trying to do remote telemanipulation, you can actually scan the scene. You've got, the robot has a model of the scene, and now you can phrase the interaction at the level of moving objects around in the scene, not just raw motion in terms of the robot. Or if you're doing this particular task, it's a task which has extremely poor ergonomics. You can basically do it for a week or two, and then you have to go out for a few days because you've basically got repetitive motion injuries. So could we bring a robot into this task, which is hard to automate, but if we could have a robot doing at least some of the more injurious parts of it, person can still be in the loop, but they can do it without injuring themselves. Or I guess my other video collapsed, but retinal surgery is another area where now it's about scale. So how do we do really micro force sensing and interaction at scales that people can't perceive? And it's not just these. There are any number of places where we can talk about really augmenting human capability. So not replacing human capability, not doing one-to-one, but augmenting human capability.
But it's just difficult for robots to essentially tie knots that have the dexterity to manipulate rope.
Yeah, so there are two things. The first is that it's a complex task from a robotics point of view. It's hard to model what's going on. It's hard to solve the computer vision problem, for example, just to find the components of the task. Also, it's a small lot problem. So that actually is, they're doing cable ties for refurbishment of Boeing aircraft. And so you do maybe a few thousand of these cable ties, and then you're done with that task. And maybe a month later, you pull it out and you do it again. And so it's just not effective to think about completely programming a robot or building a robot that's going to do just that task. And this is actually very typical right now. This is actually where, in fact, it turns out the US is still relatively competitive in a funny way, which is in these kind of small lot manufacturing cases, because it's not big enough to offshore it. And there's not really an automation solution either.
You could be working in a small environment. I mean, this one isn't as cramped as a submarine, but you may have limits on what equipment can get where, right?
Yep, exactly.
Certain dexterity, just access.
Mm-hmm. Right, so you can project, basically you can project people in whatever format makes sense for that particular task. Exactly right. So I mentioned it's not just these tasks. One of the things I happened to look up the other day was the prediction for the most rapidly growing profession in the United States, and it's in-home assistance. That's expected to grow, I think, over 10 years by 70% or something like that. And again, if you think of in-home assistance, it's not about automation. It's not like you're going to give somebody a one-to-one telemanipulation environment. It's about interaction with people to help them in their daily lives. So how do you develop these sorts of interactive systems that can replace or augment certain functions as needed? And I happen to find this too. So I guess maybe there are even some third world applications of a human augmentation of robotics. I think that's made out of wood, so it's also recyclable apparently. You can throw it in the fireplace and burn it and then make a new one.
Is it real? Is it really cool?
I don't think it is. I can't tell actually, but I just found it and I couldn't resist. Anyway, so I think there are a number of opportunities where, because of where we are now just in the technology curve in terms of sensing, computing, and robotics, we can start to think about these interesting mixes of people, devices in the physical world, sensing of the physical world to do interesting things. So a lot of our work has been in medicine. So you guys asked a lot of questions about the Da Vinci robot, so you kind of get how it works. So we started to look at it, and we realized that it's really a unique opportunity. And the reason it's a unique opportunity is because for the first time, you're really interposing between the doctor and the patient a computational system. And what it means when you've got a computational system is not just that you can program that system, but in fact, that becomes a data collection device as well. We can build a complete record of everything that happened in a procedure down to the minutest motions, most minute motions that the doctor made inside the patient. And so we actually have developed a data recording system that now allows us to make those records. And if you think about it, we can start to study how humans perform interesting manipulation tasks in the real world now at scale, hundreds of thousands of procedures in principle. And you can immediately see interesting things. So for example, this is an expert surgeon doing a simple 4-throw suturing task. You can actually see 1, 2, 3, 4 throws. This is someone who knows surgery. They've actually used the robot before. They're just still in their training cycle, and they're doing exactly the same task. And so you can start to realize that what you'd really like to do is to take somebody who looks like this and make them look like that as quickly as possible through whatever types of augmentation, teaching, or training that you'd like to have. So you can start to think about a space of task execution and skill in ways that you couldn't think about before.
So this is a position measured inside the body, surrounding the body.
This is a training task, so it's not inside the body, but in principle, yes. Exactly. And I'll show you, in fact, in a little bit what that task is. The other thing that's interesting about surgery, though, or medicine in general, is that it is a highly structured activity, and it's actually fairly repetitive. So this happens to be the flow chart for a laparoscopic cholecystectomy, so taking your gallbladder out. And you can see it's highly stylized. There are major areas of the operation, and then you can break that down into sub-areas, all the way down to dissection of specific anatomic structures. And so it's not just that we can get a lot of data, but we can get it in a case where there's actually a fairly known and taught structure to the procedure. So it really lets us study it both from the data side and from the side of understanding semantics or structure. And so we call this the language of surgery. How can I take data from a robot and parse it into this sort of a breakdown of a task? So just to give you a concrete sense of this, here's, in fact, that 4-throw suturing task is a training task. So you can see, you can sit down and you can identify, in this case, roughly 8 basic gestures that take place. And this is the way that if a doctor were teaching it, they tend to break it down and to teach it. And then you can say, well, how do we model a task like that? Well, language of surgery kind of suggests a natural thing to do would be to start with some of the ideas from speech and language and say, look, we know that we've got a set of hidden states, which are gestures. We've got a set of observables, which are the video and the kinematic data from the robot. Can we train something like an HMM to actually recognize what's going on? And presumably if we can recognize what's going on, we can now start to analyze what's going on in interesting ways.
I guess the language for the surgical robot will be different from language for the human doctor, right? Because of the physical constraint on the robot.
Well, so that's an interesting question.
I just wonder. I guess you cannot replicate everything a human can do.
No, you can't. No, you can't. You can recognize. I would argue you can recognize almost everything the human is doing. Whether you can replicate it is a slightly different case. So the interesting thing, I think, in what you're saying is, suppose that I were to give all of you video from surgery. I'll bet whether it's open surgery, laparoscopic surgery, or robotic surgery, you could very quickly recognize when they're suturing, even though you've not really seen it before, because you have a kind of a high-level semantic model in your head of what suturing means. And you could probably even break it down into kind of sub-pieces of what they're doing. So in some sense, this part is invariant, I would argue. The language is invariant. What changes is how that language gets expressed in the device or in the domain that you're actually operating in. And we've actually seen this. So we've applied this not just in robotic surgery, but in laparoscopic surgery and now in retinal surgery as well. So we also, by the way, had some belief that this would work, which was about 10 years ago. We did a very simple test in retinal surgery, in fact, and we found we could actually use HMMs to parse, in some sense, what was going on. So we actually, just to kind of, again, give you a sense of how this goes, so what you can do is you can have people sit down, you can have them do a training task like this, you can record it, so you know everything, again, that happened. And in fact, you get a lot of data out of the robot. It's not just the tooltip position, it's the entire kinematic chain, both master and slave. So it's really a lot of data. And you can do this for multiple individuals. You can repeat it several times. So you can get a kind of repetitive data set of people doing this. Just like if you were training speech, you would get a lot of speakers saying the same sentence, for example. So you can start to learn the language model. So we do the same thing. And in fact, if you do just experts and you confine them to a fairly constrained task, you can do extremely well at recognizing what's going on. So this is the difference between a manual labeling and an HMM segmentation of that 4-through suturing task into the gestures. And the main thing you can see is, obviously we've nailed it in terms of the sequence of actions. The only real difference is these slight discrepancies at the boundaries, trying to decide when they transition from one gesture to the next. So when you see me give accuracies like this 92%, what I'm really measuring is how often the blue line and the red line are perfectly lined up. So here, 8% of the time they don't line up, and that's what we consider the error. So that's good. So what if you try to do this a little bit more in the wild, which is get a wider range of individuals and you get a wider range of tasks, and you do the same thing. And these are, again, pretty standard training tasks in robotic surgery. So this is a data set we collected a few years ago. And the first thing you find out is if you just take standard HMMs and you try to apply them here, they don't go. They just don't generalize well as the data gets more diverse, which is probably not a big surprise in the end, but at least it was the starting point for looking at this. So then we started to figure out what's going wrong here. So part of what's going wrong is we've got really very high-dimensional data relative to what we're trying to recognize. And in fact, at different times, different pieces of that data matter. Sometimes knowing where the tool is moving matters. Sometimes knowing how the wrist is being used matters, for example. So we embroidered the HMMs a little bit. So these are factor-analyzed HMMs where there's basically a dimensional reduction step that's taking place off of the hidden discrete state. And in fact, once you do that, you start to see your numbers pop up. So we've gone from 54 to 71%. But there's still a little bit of a bugaboo. And that's this, that you might wonder what is setup 1 and what is setup 2. Setup 1 is more or less standard leave one out training and testing. So I just take one trial and I throw it away, train everything, and then I test. But there's a problem with that. Anybody guess what the problem is? See, now I'll go into lecture mode here. Oh, it already says. There you go. Yeah. You need to, this happens to me in class all the time too, by the way. And sometimes I still get it wrong. That's the amazing thing. So yeah, we didn't leave one user out. So what it's getting to do is it's getting to see the entire user population and then basically recognizing. As soon as you take one user out, you see things drop pretty quickly. And so it's overtraining in some sense. It's learning to identify people for all practical purposes, which in itself is interesting. This is a useful thing to keep in your head. So this is what the parsers look like again. This is a good one, so you can see, again, things overlay pretty well. This is a bad one. But notice that if I look at the sequence is actually just about perfect. Really all, again, that's happening is it's kind of arguing about where the gesture changes take place. So that's something useful to kind of keep in the back of your mind for later. So we weren't happy with this, so we started to look at other ways that we could improve this. And so there are two things that we've done, both of which right now seem to give pretty good and about the same results. One is to go to a switching linear dynamical system. And so the only difference is we're going to take this, this hidden state, and we're going to add some dynamics to it. Or another way to think of it is, instead of saying that we're going to view each discrete state as essentially having a stationary distribution associated with it, now it can have a little dynamical system that changes a little bit over time associated with it. And that has its own dynamics somewhat independent of the discrete state. So if we do that, things get a little bit better in the leave one out case, but they get a lot better in the leave one user out case. And so it seems to be capturing more the essential aspects of the data and not overtraining into a single user. And then another bit of work, this is really René Vidal's group did this, is looking more at a dictionary-based approach. So instead of just trying to train straight from the data, first develop a dictionary of motions and then build the entire training apparatus on top of that dictionary. And in fact, if you do that, you get really roughly about the same performance. So these two kind of are about equal from the kinematic data. What's interesting about this method is if you look at the video data. So this is some work that appeared in Mackay last spring, where we took the video data, not the kinematic data. We did spatial temporal features on the video data, and then we trained up these models using the video spatial temporal features. And so if you take something like this dictionary-based HMM on the kinematic data, these were the sorts of numbers we had. But if you now go to the visual data and you do a little bit more embroidery on the dictionary-based methods, you can actually start to get numbers which are getting back to that first set of trials that we had. We're now looking at kind of 90%-ish, 80 to 90% recognition rates. Interestingly, if you add the kinematic data in, it goes down a little bit again, which probably kind of makes sense because the kinematic data had a lower recognition rate to start with, and so it's confusing things just a little bit to put the two together.
Kinematic data is the positions?
Yeah. Well, it's all the tooltip positions, velocities, the rotational velocities, orientation of the tools. It's about 190 different variables. It includes things like the gripper opening and closing as well. So when I say kinematics, I just mean anything to do with any joint in the robot moving one way or another. But we're getting pretty happy with this now. So we've actually managed to scale it up at least to a more diverse group. Yeah?
What's the visual data?
So the visual data, I'm sorry, I was going to get the video from René and I didn't get a chance. The visual data, so we're taking the video and we're doing spatial temporal features on the video. So in every frame you're computing something like a SIFT feature, but SIFT in space and time at the same time. So you get that group of features together, you learn a dictionary on those features, and then you build a dynamical system around that dictionary.
So what do you gain with it? I mean, the position, the instrument, you have all the information from the kinematics. So what are you gaining on the visual is information about the patient?
I wish I knew what I gain in the video. So what I probably gain in the video, you're right, is maybe the best way to think of it is this way. So when I learn from the kinematic data, it's like learning pantomime. Right? I'm just looking at hands moving and trying to guess what they're doing based on the hands are moving. When I get the video data, some of the features are from the surface as well, and so I get contextual information. I now know that the tool is moving to the suture site as opposed to the tool is moving in a straight line. I can only infer that it's moving to the suture site. So that's my hypothesis, but it's machine learning, right? So there's a black box, and I haven't figured out how to open the top of it yet. But this really is starting to put us, as I said, in the ballpark of really being able to use this data to recognize what's going on in diverse individuals. So what can we do with that? So I mentioned skill before. So what is skill? Well, right now, skill means that you stand next to a doctor, an expert, an attending physician who's doing surgery. You learn through apprenticeship. They watch what you're doing. They give you feedback, and eventually, after roughly a year of fellowship, for example, they'll say, okay, you're now a surgeon, go do surgery. Today there's getting to be a lot more interest in saying, well, can we define that a little more formally? How do we assess skill? How do we know someone's qualified to be a surgeon? Or how do we do reassessment? So, how do we recertify someone as a surgeon? So, for example, this is something called OSATs. where what you do is you go through a set of stations and you have a set of basically skills you have to practice, and there's a checklist, and somebody can more or less grade you on your skills, and you get an overall score. But this is still, this is problematic. You got to set all these things up. You've got to have somebody who's basically licensed to do this sort of evaluation. We'd like to say, well, could we get it from the data itself? And you can actually see stuff in the data that correlates with skills. So for example, if you just look at the sequence of gestures that an expert uses, they look very clean, right? They're linear, they start at the beginning, they go to the end, they don't go back and forward using kind of intermediate gestures. And this is what a novice looks like if you take those basic gestures and you just plot how they use the gestures. So clearly there's something here. And in fact, if you just do, you take that and you just project it down into a 2D space, you can actually see pretty quickly that experts, intermediates, and novices start to separate in the space. So we can actually start to see where you are in the learning curve of surgery from these models. Now that's using what we call self-declared expertise. It's just based on how long have you been using the robot, how much training have you had. You can also do something like OSATs on the data. You can have someone actually grade the task that they did. Interestingly, it's much harder for us to replicate OSATs using these techniques. So we drop from about 96% to 72%, chance is 33%. And you can see if you do the same sort of collapsing that things kind of cluster together more when you look at the by trial performance as opposed to by self-declared expertise performance. So we've been thinking about how to think about capturing skill a little bit more precisely in these models. And we think we have something now that's starting to work. This is still in evolution, but what we've done is we've adopted a different coding scheme for the data. So one of the problems that I've been complaining about to my group for a couple of years now is that we're working from the raw data itself. So it's a little bit like saying, I'm going to take the raw recorded speech signal and I'm going to try to parse it into phonemes. Well, you don't do that in speech, right? You take the raw signal and you do vector quantization of some sort on it, typically, and then you start to do phonetic recognition. So what's the version of vector quantization for this? Well, think of this. Suppose that I take just the curve you saw and I build a little Frenet frame at a point. So I can compute the tangent, I can compute basically the plane of curvature that gives me two directions. The third is now defined relative to those two. And now I can say, well, what's the direction of motion over a small time unit relative to that local frame? Now this has a lot of advantages, one of which is now I'm coordinate independent. So if I'm suturing up here or down there, it doesn't matter. The code is the same. And it also abstracts the motion a little bit more. And so we've actually found that using even very simple sort of dictionaries based on these Frenet frame discretizations, we can push our recognition up much further. And the way we do it is we discretize and we actually look for the substring occurrences in that data. So you'll get a long string of symbols. You say, what are the repeated substrings? Experts tend to have long repeated substrings. Novices, much shorter and different repeated substrings. And so we can build very simple string kernels, string comparisons, that actually get us now, again, kind of in this 90% plus range, which is where we start to feel like we're actually understanding what's going on. And in fact, we can do both gesture and expertise, which is interesting, because now we can actually break it down and say, well, what gestures are you doing poorly, and which gestures are you doing well? And I can illustrate why you might care about that. I'll show you a little illustration. This kind of goes now towards teaching, which is what I've done here is I've got two videos, as you can see. Both of these are experts. And what's going on is we're taking the video, we're stringifying it, and then what we're doing is we're playing the videos together when the same symbol is occurring. Okay, so you can kind of think of it like if they're speaking in unison, the videos play together. If they're saying something different, one stops and the other advances. So it's almost a visualization of edit distance, if you will. And what you can see is experts really do converge to a pretty consistent model. They're running at about the same pace. They're doing about the same gestures. There's not a lot of pausing, except this guy likes to readjust the needle a little bit, and so you'll get a little bit of pause there. So that's cool. So it shows we can align a couple of experts. What about if I take you and tell you to do this task and sit you down at the robot? What can I do now? Well, so there goes the expert. There's the novice. Actually, you probably could have told me that already, right? So you can see it's not so easy, right? Well, so there are a couple of things interesting. I mean, obviously, yeah, it's a little scary, isn't it? Luckily, that's a grad student. It's not a surgeon.
They call this teaching hospitals?
Well, so here's the interesting thing. There are two things here. So first, just to make a quick point here. So this person is doing things completely differently, right? I mean, they're holding the needle differently. The motions are different. But we can still align them. And that goes back to that diagram I showed you before, that we're getting the gestures right in the right order. And we can even do it when there's this wild style variation. The other thing is, and this goes to the teaching hospital point, that one of the problems with robotic surgery, and I think this is going to be generally the case as we go to these more collaborative technologies, is it's really hard to teach people because you can't stand next to the person and say, here's what you should do. You're sitting in a cockpit, in this particular case, doing something, and at best the expert can be outside saying, oh, you're holding the needle wrong there, you should fix it. But they can't reach down and say, okay, here's how you should do it, at least not when you're inside the patient.
But they can have the same video feed.
They can. So they can show what's going on. But here, what I can do is I can basically just put the expert in the bottle, right? I can record that video. You can start to do the task, and I can immediately detect when you start to diverge from what an expert would do, and dare I say, have a little paperclip that could pop up and say, are you trying to drive a needle right now? Could I help you? That may not be the best example, but you see what I mean. You can build now basically a dictionary of what everybody ever did, inside a patient in a training task or whatever. And you can start to detect the variation, and you can offer assistance, if nothing else, by saying, here's what an expert did at this particular point in the procedure. And so it becomes basically a way to do bootstrap training. And also, you can do it at this level now of gesture even. So I can detect it's the needle driving that's the problem, because you're holding the needle wrong and you don't have good control. The rest of the tasks are actually doing just fine. They're passing the needle as well as the expert did. And so you can actually do now really what I think of as interactive training for these tasks. I'll give you one other thing you can do with it, which is I can also learn to do pieces of the task autonomously if I want to. I've got a discrete breakdown of the task again. Certain parts of the task are pretty easy to do, like passing the needle. So why don't I just automate that? So here's a little system we built. This is Nicola Pedoy, a former postdoc. So you can see this switch probability. So there's a little HMM running behind here, which detects when you're in an automatable gesture, and then it switches control over and effectively plays it back. And the trajectory is actually a learned trajectory too. So you sit down, you do the task for a couple of dozen times. The system learns the model both in terms of the discrete states, but also it does a regression to compute trajectories for these automated trajectories. So you learn the model, you break it down into things you want to automate, learns the trajectory, and now, again, it pretty reliably recognizes, in this case, when you're done driving the needle, and then it says, okay, I could do that automatically if you wanted me to. Again, I'm not advocating this is the way you want to do it, but at least illustrates the concept that the system is capable of now changing how the robot acts or reacts based on the context of what's happening within the procedure. So, putting it all together, we actually can start to build these systems which work together with people, and they actually have measurable impact. One of the nice things about this is it's not just that I can build it, but I can say, well, did it change anything? So in this particular case, it reduces the amount of master motion that you need to do, or the amount of clutching that you have to do, which actually turns out to be important in terms of efficiency. We can go one step further with this. We talked about the fact that we don't have perception in the loop. So here's a couple examples of building perception components that we've picked up. And we can start to look at, well, how could we use perception to provide even more context and make these things even smarter. So I'm going to actually use the 3D object recognition side of this. And so we did actually some experiments this summer. This is what we call perceptive teleoperation. So again, Da Vinci console, in this case, it's wrapped in ROS. It's connected to a robot which is over in Oberpfaffenhofen, Germany, in the robotics and mechatronics lab there. And so we were interested in saying, well, suppose you're trying to do these tasks, and for whatever reason, you've got a poor communication channel. You can't really get the information across either with the bandwidth or the delay that you need to do the task efficiently. Can we use perception to augment the performance? And the idea is to say, well, again, if I can recognize what you're trying to do, and I've got a perceptual grounding for the task, I can automate or augment some part of the task around the perceptual cues that are there. So this is a little, this is actually work that's going to appear at the Robotics conference in May. So this is the robot in Germany. It's being teleoperated from Johns Hopkins on a Da Vinci console, in fact. And this is without any sort of augmentation. And there's about probably a quarter to half a second time delay, just depending on what the internet happens to be doing at any point in time in this. And so you can see you end up in this move and wait sort of mode where you move as far as you think you feel safe, and then you wait for a little bit. This is what they do with the Mars rovers on Mars, right? They move them a couple of meters and they wait 20 minutes until they see what happened, and they move them again. And in this case, so the operator grabbed it, but in fact they didn't have very good orientation, so this thing kind of swiveled and moved, and in fact in some cases it'll actually fall apart. So now what we do is we turn on assistance. It actually parses this structure. This little orange line says, oh, I see a grasp point. It recognizes you moving to grasp, and it simply automates the grasp. And so now you've got it in the right sort of configuration. It happens relatively quickly. And now you can go back to whatever task you want to do. And it simply automated that little bit of it. And again, you can measure the difference that it makes. So in this case, it just about doubles the time, or halves the time it takes to perform the task. And in fact, the same idea now is what we'd like to do in that little knot tying task that we talked about. Breaking this down into component pieces. So one of my grad students, I said, just as a benchmark, use the Da Vinci and see if you can do this task. So you can see he's using all three tools on the Da Vinci in this case. So you've got to switch between tools to do it. So this took, we could time this. It probably takes, 20 seconds or something like that for a human. And this right now takes about 3 or 4 minutes to do with a robot. And so I said, okay, your thesis is now defined. So how do you go from 3 or 4 minutes to 20 seconds with a robot? I don't know if he's going to achieve that, but at least we can start to see the sort of benchmarks we have to achieve to be in this sort of space with these techniques. So just the last thing. So I've been talking a lot about robotics, and you saw in the beginning of my talk I had also human-computer interaction using vision. And so I wanted to talk a little bit about that. And in fact, that's part of the reason I wanted to stop by today, is talk about something else we're doing, which is now still, I think of it as collaborative computing in physical space, but the physics is much more about people interacting with virtual environments than robots interacting with the physical environment. This is a display wall project. In just about a year ago, a little over a year ago, the library came to us, and they were building a new wing for the library. And to make a long story short, they wanted to have some technology focus to the library. Just by way of background, Johns Hopkins Library at one point in time actually had more digitally stored data than the Library of Congress. We host Sloan Digital Sky Survey. We host connectomics data from biology. This happens to be scans of some medieval French manuscripts that are in the archives. So terabytes and terabytes of data. And they said, is there a way that we could start to think about ways that people can interact naturally with data in the library space? And so we built a display wall form. This is my grad student, Kel Guerin, with his back to you, who built basically a display wall from scratch. Starting in about December, come up with the physical design, the electrical design, wrote all the software, and we opened it in August and we dedicated it in October. So basically 10 months from conception to completely running. The reason, again, is that our library really thinks of this as a way to start to think about how people will interact with information in the future and how research will be done around these large data archives. And so this is what it looks like. So it's about 12 feet wide. You can see it's running 3 connects for gesture interaction. This is the kind of the opening screen that you walk up to. It's just a montage of images from Hopkins. So you walk up, it sees you, it builds a little avatar out of the images, and you can kind of play around with that if you want to. And then we use this curious put your hands on your head gesture, and you get a fairly rudimentary but still workable user interface into a set of applications that you can now drive using gestural input. And part of what we're after here is not that these are the best applications or the user interface is done as well as it could be, but it's really interesting that it's out in the middle of the university and about 10,000 people get to see it at various times during their academic careers. And so our goal here really is to think of this as a lab. It's a lab to learn about how people might want to use technologies like this and then try to run after them and figure out what do we need to make this technology useful for them. We, of course, had to have a video game. So when we went live, we've got basically an image viewer, a video game, and a couple of other kind of image modalities. I was hoping I would have this to show you. We actually figured out how to load CAD files of buildings in that, so you can start to do walkthroughs of buildings, basically at scale, using spatial interaction. So it really is completely a work in progress, but it's now kind of flipping around and letting us use a lot of the same ideas and technologies, but thinking of it more from people interacting again in virtual space. So for example, if you're doing something in biology, there's a natural task. If I'm doing molecular design, there are things that I want to be able to do, manipulations I want to take place, that's my task. I want to parse that, and then I want to do anticipatory computing to say, well, if they're trying to move this particular binding site over here, how can I actually run a simulation that will check and see if that's a reasonable thing to be doing at this point? So part of it is just exploring that level of interaction. We've had people already come to us and say they want to do art and dance, so they want to make the system react to people doing like a dance performance in front of it and make that part of the display. Crowdsourced science, so we're trying to put connectomics data on it and let undergrads be labelers for biology data. We need, it's basically like Mechanical Turk, except now with undergrads. And the payoff for them is we say, look, if we publish a paper on this, you're a co-author. So I'd say my goal is if I could publish a science paper with a large fraction of the undergraduate population at Johns Hopkins, then that's my win.
People will be filled by all the undergraduate names.
Well, so there are physics papers with over 1,000 authors on them.
Oh, really? Wow.
Yep. So I was actually talking to these huge experiments, right? I mean, it's a
crowdsourced paper in Science that has something like 10,000 authors.
Yeah. Hopkins is a research university. We advertise the idea that undergrads should get involved in research. So what the heck? Here they go. And actually, we've got. I see I can't spell, can I? These French medieval manuscripts are actually motivated by an art historian who wants to do research on those manuscripts and needs something that allows them to interact with the data with the sort of visual scale that the wall can give them. So I really think of it as it's really just this lab sitting in the middle of the library, and it's just trying to create the idea that people can do this as a project to create new ways to interact with data in their field. Just to give you some anecdotes about it. So we're getting about, right now, 10 to 50 sessions a day. It started out at about 500 a day, in fact. We've got about 10 students a semester right now that actually come up and say, I'd like to do something with the display wall. We get about, on the average, about one query a week from somebody in the Johns Hopkins community saying, I'd like to build something that could run on the wall for my research or just for whatever personal amusement I have. And we're actually starting to get sites at other libraries, in fact, that are calling us up and saying, hey, could we put this in our library as well, and would you be willing to share the code? I don't think that most libraries don't quite understand that this is not quite as much of a turnkey operation as they might like to think. But it's interesting that a lot of people are latching onto this now. So let me just kind of close by saying, so I started out by saying that, you know, I think the world is different today than it was 10 or 15 years ago. And it's really different because of the platforms we have, the computational tools we have, the output devices. You know, that display wall could not have been built easily even 5 years ago, probably the way I can now. And so we really have to think of what does this mean as, you know, the world has become porous to computing. You know, just about every aspect of life can cross the barrier from the physical world into the computational world and back again. So how does that change how we want to think about computing? So one of the things that I'm thinking a lot about these days is, you know, what does it mean to program these sorts of collaborative systems? You've got hundreds, thousands of different things that you would like these robots or these display walls to do, and you can't have a computer science student sitting there next to somebody every time saying, okay, here's the code that's going to make this application work. So how do you think about combining what I think of as programming in a schematic sense, saying, look, here's the thing I want to do, with probably some learning and adaptation that then says, okay, now here's how it gets customized to what I'm trying to do. So in the robot case, for example, if I'm doing small lot manufacturing, I know the manufacturing steps, I know roughly the handling that has to take place, build the schema, and then run through it a few times manually in a training cockpit, like you saw with the Da Vinci, have the robot kind of fill in, or the system, I should say, fill in some of the details, and now I've got a workable program. But what's the paradigm around that, and can we make that something that's accessible to a broader group? Shared context is important. If we want these systems to work with people, there has to be a shared notion of task and context. I think I already said what's key also is that we have to have these platforms in the wild, because we have to see what people do. It's you know, I always said I used to have, you know, things like the display wall inside the lab, and we'd bring people in and they'd be really excited and they'd play with it and they'd go away. Having that display wall out in the world, we spent 2 weeks, we had a soft opening, so we had the wall up for 2 weeks before classes started. And it was incredible how many revs we went through in that 2 weeks, as we just watched people use it, kind of fix things, change things until it got to a stable point. So we really have to test these things in the wild. And then I think the key thing is, once we have this, creating interfaces that now really do focus on interaction as opposed to input-output. So thinking about how do I anticipate what's going on and adapt to it, essentially. Thinking about interfaces in terms of a dialogue as opposed to, you know, I type something in and something comes back to me. There's state, there's history, there's intent around it. And I think the great thing is there's a real reason to do it, right? There are real tasks, there are real industries, there's economics that can actually drive this. So I'll just close by saying, you know, I think we're living in such a cool time, you know, and I'm so glad that I was here actually to see it. I think, you know, computing keeps reinventing itself, but at least relative to what I do, it's now suddenly in a state where we can do all sorts of things that I just couldn't have imagined even 10 years ago. And so with that, I will thank probably a subset of my collaborators at this point in all these different projects. I will also thank the people that support me to do it. And maybe I'll just leave you with that final thought about where we may be going someday. All right, thank you very much for your attention.
Thank you.
Just a question. I'm still wondering why the robotics talking about and stuff on the robotics side where so you have this kinematic data versus the spatial data. So it reminds me of this. So we'll work with Connect, right?
Mm-hmm.
So we'll have this skeleton data, and
right.
then also have the depth map. So like even the depth map and also even the GB data. Right?
Mm-hmm.
So sort of your skeleton, your kinematic data is kind of like skeleton data.
That's right, exactly.
Right? So, but for Connect, sort of the I noticed that usually the Connect skeletons which don't capture everything. Right? So that's why sometimes depth maps plus do better
Right.
than just skeleton data. But I wonder if that's kind of the reason that you don't get good result. Kinematic data, I wonder if that has the same reason.
No, it is, absolutely. I mean, well, so I should say, so the kinematic data has super high fidelity. You know, I know, yeah, oh yeah, I know where the tools are to, fractions of a millimeter, at least in relative motion. But what they're missing is the context. So, the analogy would be if I had a skeleton, the skeleton doesn't tell me if you're holding something.
Right.
And I might be able, within the context of a task, to infer that. Like, if I see you reach down and see a pick-up motion, I say, okay, they probably just picked up the briefcase. That's part of whatever they're doing. But with the video data, I can confirm that, and I know that. And I know whether you succeeded or not, for example. So in fact, like one of the projects that one of my students is playing with just to kind of get warmed up is, can you detect whether or not, in a fairly automated way, what the gripper is holding? So needle, suture, if it's in proximity to tissue, but do it without hand tuning something. Just get a few million snapshots and then correlate kinematic data to what you see in the image, and then learn something about the set of states that the gripper can be in. And just that little bit of information can make a huge difference. And we already know that from some manual tests.
So you've been hinting at moving from this pure one-to-one manual task to sort of manual plus automation, plus obviously heading towards automation. Just curious where you're. So let's say you have this gallbladder removal procedure, fairly standard thing, I guess.
Yeah.
A friend of mine here just had that done by a robot a week or so. 20 years from now, I don't know, is that going to be a one button? Is it going to look like that? Or is it going to be, I mean, I don't know where, where you sense that
no, for a couple of reasons. One is no, I think technically that would be incredibly challenging to do. And no, socially, because I just don't think it's an acceptable solution. So it's always going to be a human-in-the-loop system. And I think what I imagine more happening, so to give you an example, the sorts of things that we think about doing. So one of the procedures that is still on the cutting edge of robotic surgery is laparoscopic partial nephrectomy. So it's removing a tumor from the kidney laparoscopically with a robot. And it's challenging for a number of reasons. One is the way you do it is you burrow into the kidney, you expose everything, and then you clamp the feeder valve to the kidney, and then you go and excise the tumor. And when they do that, they start a clock. And the reason they start a clock is because it's well known that after about half an hour, kidney function just drops off like crazy. And the reason you have to clamp it is because if you try to cut the kidney when it's fully, when you haven't done that, it bleeds like stink. I mean, you just can't do anything with it at all. So you've now got this really constrained thing. You've got to go in, you've got to cut out the tumor, you've got to tamponade it, you've got to suture it. And so we look at places like that and say, okay, what pieces of that could we provide some sort of augmentation for? And it's not just physical. So we provide a dissection line. So we can actually, I've got a video where I can show you, we register and we show you here's where you should dissect to get a reasonable tumor margin. We can actually start to, in the suturing case, we can start to automate. So you have to really use 3 hands to suture, and so you've got to switch between hands, and that takes time. So if you can automate the movement, retraction, any piece of it, you can basically shorten that time, and that improves outcome and reduces the difficulty of the procedure.
You're also thinking along, so with airplanes, right, and like automatic flight, like they don't let you, for instance, put them into a stall. Like, are you thinking, are there possibilities for kind of tapping someone on the shoulder saying, stop here, like I can do that, or?
So my dream is if you had these 300,000 procedures and you had them all basically in a dictionary, as it were, and you're going along, you can always be comparing what's going on now to what happened in other cases. And you know the outcomes of all those cases now. So you can start to predict, okay, given where you are and what you're doing, this isn't looking good anymore, and by the way, here's the closest example to what you're doing, and here's what happened. And so you really could start to have, again, the paperclip's not the right model to think of, but something that at least could have a little icon that says, you've deviated from standard procedure here, you may want to check what you're doing and think about it.
The other thing with like thinking again of airplanes with like semi-automatic, and I understand that maybe surgery is not going to get that automatic that fast, but it's the transition points, right?
Yep.
Where you go from and back, you know, to the that's challenging. I think.
Yep,
And
it is. So situational awareness. You know, the thing I've been thinking a lot about recently is automated driving, because everybody's saying automated driving is going. And you know, you can imagine having an auto-driving car which does great until it gets into a situation that it doesn't understand. It says, well, I don't know what to do. Here, it's your problem now. And so suddenly, you know, in the middle of barreling over a cliff, it's your job to suddenly take over driving. And that's unacceptable. And I think that goes, though, to this contextual awareness and a task and anticipation of saying, it's not just can the system do it, but should it do it right now? Because doing it right now might put the human in a position that later on they don't know how to recover from.
I guess you're in computer science.
Yes.
Do you know what's going on in the, let's say, the mechanical engineering, control theory guys in terms of teleoperation, especially with delay? Because that really speaks to, I would think, having this delay, you have to do something locally, low delay, which would mean some kind of intelligence. You know, are they doing anything that will address the sorts of problems you're looking at?
Well, so that's another one of my hobbies right now, in fact. So what a lot of the science around this in that space right now is looking at things like how do you actually prove properties of systems with time delays, for example. So I can prove passivity of a system, and if I have a passive system, even with time delay, the system will not go unstable, which if you're doing surgery, you obviously would like to be able to prove that your robot won't go unstable inside the patient. What is missing, I think, and this is something that this is kind of my glass of wine conversations, is if you think about doing those tasks, there's a certain amount of information you need to perform a particular task. You know, what are the objects in the environment? You know, what are their orientations? Where am I trying to put them? How much do they weigh? Who knows what it is? And if you're doing full teleoperation, you're assuming that all of that information lives in my head, essentially. And I have enough capability to get movement information to the robot to say, here's how you perform the task using what's in my head. If you want to start to automate pieces of it, what you're doing is you're moving information into the remote side. So now the remote side plus you have to have enough information to perform the task. So I think there's really this notion of information invariance around tasks, which says, you know, I could fully automate it if the robot had every piece of information relative to the task. It probably doesn't, so a piece lives with me, a piece lives with it. Now, how do we prove properties or think about properties of systems where information lives in both places and the sum of the two pieces is enough to perform the task? That's not something that as far as I know, the control theory people are thinking about right now. The practical solutions right now, I'll tell you, are mostly anticipatory. So you try to predict what's going on, and you feed forward the robot, but you try to do it in such a way that you can maintain safety. Yeah?
So one question in terms of data collection, because you mentioned that you have collected a lot of data using video and surgery. I wonder if you're able to make this data available.
I can't make the robot data public because that's actually governed by Intuitive Surgical. I have an agreement not to share their data with people. Other surgery data, sure, modulo IRB concerns, so privacy concerns, sure, we could share that data.
Do you usually publish your data in your website? Or
not until now, and that's largely because, again, I have to do these sorts of studies, they involve humans, so I have to get institutional review board approval to do it. And if I put it out on the website, I would go to jail, so I kind of try to avoid that. But I can actually ask them for permission to do it, and we've done it in the past. And so we probably will.
This is a new order by the president. It's all the fund project data funded by the government should be public, right?
That's right. That's right. So that'll create some interesting tension. Well, the other thing, and I'm sure some of you know this, data is gold, right? So if you have data and you have not yet kind of mined that data, so it's really a question, what's a reasonable period of time that you have to exploit a data archive before it has to be made public?
especially it's very hard for us to get the data from observer surgery. So
possible to really get it.
Did you watch the Academy Awards yesterday?
Oh.
I stopped by Rick's house just to see the piece de resistance.
We worked at the house of Michelle.
Obama was on the screen.
So that's the part we saw.
So there was a teddy bear in the show, which I have no idea whether it was computer graphics or a robot. It was too small to have a little person or something.
Probably teleoperated. Probably teleoperated would be my guess.
It walked out and
Okay, walking out the chair.
climbed up a stool.
Yeah.
Oh yeah?
And
Walk
sat
around
up there
really
and it
quickly.
talked. And
Oh,
everything.
okay.
I was
Well,
thinking-
then, yeah.
I was thinking, anyway, I was curious.
I'll go check.
what
It's got to be
your
on
guess-
YouTube by now, I'm sure.
Curious what your guess is.
Was it related to that movie? There was a movie.
Yeah.
Yeah, the movie. Yeah.
I'm curious what it is. I wanted to see it again to try to start picking apart whether it was computer graphic pre-rendered or what.
Interesting.
Fun little robot.
I have a question regarding that large display on the library stuff, so which is very cool. And I have two questions about that. The first one, I'm wondering about the user's usage. So most students use that for playing game or use that to get information about the, And my second question is, have you observed any frustration from the student to using the system? And what that frustration, if there is, what that frustration comes from the interaction or come from the how to navigate the library?
Well, so these are the usage statistics. By the way, this is the dedication day, so that just about got the highest usage. So usage right now is running, I think I was saying 20, 30 sessions a day. Most people play the video game. About a third of them use the image visualization app, and about a small number of them just kind of go through some of the other how-to stuff on the wall. And that's actually, I'm kind of surprised this isn't bigger. So I'm pleased that they're at least looking at images. And we've got some really nice images, so it actually is fun to do. I'm sorry, what was your second question?
Second question, have you observed any
frustration. Yeah, my frustration is the gesture recognition works not as well as I'd like. But I will tell you that, so when we started the wall project, we look at both Windows and then at open source. For a variety of reasons, we ended up going open source. So we're using Knight as the gesture recognition software. We're not using Microsoft. So my firm belief is that if we were to run Microsoft software, it would all work perfectly.
Is there any sort of, because it's a large space, do you guys support any sort of multi-participant interactions with that? Yeah.
Most of my interest, quite honestly, is in multi-participant collaborative interaction. So how do you have three people solving a problem together with computation behind it? And in fact, nothing for the wall is one-to-one. It's all multi-to-one.
So I have a question regarding the evaluation of the training session. There's no absolute ground truth, right? So the ground truth used is the self-assessment of the searchers.
Yep.
Usually people are overconfident about their skills.
Well, no, so I don't. So we don't do self-assessment. So people do tell us what experience they have, and we do compare with that as well. But we actually have some clinical collaborators that go through and they do an objective assessment of the data. So that OSAT score is done by someone who's not part of the trial. All right.
Okay.
So we exhausted everyone?
Yeah.
All right.